Okay, 2.57 is pretty much the same thing as 2.56 and 2.55. The only difference now is that we're doing the infinite square well instead of the harmonic oscillator. So we know this type of potential by heart now, hopefully, which is that for an infinite square well, we have v of x comma t being equal to 0 inside the well, and we're going to say here that the well is going to be from 0 to a and infinity outside the well. So the wave function can only be 0 in the region where the potential is infinite. So because of that, we only have to worry about the region inside the well. And the Schrodinger equation is something we already know. Applying variable separation and all that stuff, setting v equal to 0, we get negative h bar squared over 2m multiplied by d2 psi by dx squared is equal to e times psi. So at this point, if I want to rearrange this into an actual second order differential that I want to solve on Python, I'm going to do d2 psi by dx squared is equal to negative 2me over h bar squared multiplied by psi. Now, at this point, you could just do all the steps that we did in 2.55 and 2.56 via sort of converting this into two first-degree ODEs and then solving it, and by all means you can, that is very much possible to do. However, I'm going to take an extra step here and note that our variable of interest, which is x, is a variable that has dimensions of length. Now, it's very possible to do this problem without making this substitution, but in general, especially when you're doing online calculations, a lot of the times your problems become much simpler and less painful to do if you turn your variable of interest into something that is dimensionless. So in 2.55 and 2.56 we didn't do this because the substitution that was assigned to us didn't have this property. It did have a dimension, but we can do it here to make the system just more simple. In this case, because of the fact that the infinite square well is already such a simple system, it's not really going to make that big of a difference, but it's a good practice to get into the habit of doing, because later down the line you're going to have a lot more complicated problems, and doing this sort of substitution when you're trying to solve differential equations online can sort of make your life a lot less painful for specific problems. Not just specific problems, but just in general more complicated problems. So I'm going to make the substitution of chi being equal to x over a and redefine my wave function in terms of chi instead of x. So in that case, if I do this, then by chain rule we have d psi by dx is going to equal now d psi by d chi multiplied by d chi by dx. And d chi by dx is just going to equal 1 over a, so this is equal to 1 over a times d psi by d chi. Then the second differential, d2 psi by dx squared, is going to be d by dx of d psi by dx, which is going to be equal to d by dx of 1 over a d psi by d chi. Via chain rule once again, this is going to give us I wrote my derivative partial the wrong way, d chi by dx times d by d chi times 1 over a d psi by d chi. Plugging this in, this gives us 1 over a squared times d2 psi by d chi squared. So if we do this substitution, then our new wave function equation is going to be d2 psi by d chi squared. And then we have the 1 over a term, or 1 over a squared term, which I'm going to move over to the right to give me negative 2m a squared times e over h bar squared multiplied by psi of chi. Now at this point, the next thing we do, we have to assign boundary conditions. So initially we have the boundary conditions that psi of x equals 0 is equal to 0, and psi of x equals a is equal to 0, because remember, the wave function has to be continuous. So as we go from the beginning of the well to the end of the well, the wave function has to go to 0, because the wave function is 0 everywhere outside the well. If we want to convert this in terms of chi, then we get chi is equal to 0 over a, which is equal to 0 over the first boundary condition, and then chi is equal to a over a, which is equal to 1 over the second boundary condition. So our new boundary conditions under chi is going to be psi of 0 equals 0, and psi of 1 equals 0. Now, at this point, we would normally do, ODINT on Python as we've done on 2.55 and 2.56. There is a slight problem, which is that ODINT can't actually work with non-zero initial conditions. And what I mean by that is that the standard initial conditions is that psi of 0 has to equal something, and then psi prime of 0 has to equal something. It can't work with the fact that this term here is not 0, because ODINT only works with sort of t equals 0 as the initial condition. It doesn't work with arbitrary time points, or in this case, x points. So that's one problem, and we are going to address it later down the line as we get to it. But first, I think I'm going to actually do the conversion first. So I'm going to reassign this into 2 first-degree ODEs, and I'll worry about this problem after that. So I'm going to write u1 is equal to psi, and I'm going to write u2 is equal to psi prime. If you're not familiar with this process, look back on 2.55 and 2.56. Then our new system is going to be u1 prime is equal to u2, and u2 prime is equal, and I'm going to redefine this as k. So I'm going to say k is equal to 2m a squared e over h bar squared. So negative k times u1. So now, resolving this issue of the ODINT not being able to work with non-zero initial conditions, to resolve this, we have to look at the actual wave function, because we know what the wave function looks like. I'm actually going to post it here, because we've already solved it a long time ago, way back in the start of chapter 2. It looks something like this. And one thing that you can notice here is that because of the fact that the wave function is always going to be a sine term, it's effectively always going to be odd. And because of that, its first derivative is always positive. So what we can do instead is we can assign a new arbitrary initial condition, which is that psi prime of 0 is equal to 1. Now, this isn't necessarily numerically correct. If you actually took the derivative of the wave function, you would find that the derivative, after doing the substitution from x to chi, you'll find that the derivative of psi isn't actually equal to 1 at x equal to 0. It's equal to some weird constant formula based off of whatever the derivative of the wave function becomes. The thing is, however, that even though this isn't numerically correct, it's going to provide a valid wave function shape nonetheless. Like, the wave function is going to be on a different scale, it won't be in the correct scale, but the resulting energy values you get is still going to be the same. Because remember, wag the doll, or wag the tail, is a method that's primarily based on looking at zero crossings for graphs. And the zero crossings are not affected when we change the scale of our wave function. So because of that, we can just arbitrarily say that psi prime of 0 is equal to 1, and as long as it's just a positive constant, this can work well enough for our purposes. So I'm going to replace this with sort of our initial condition over here. Now, note that I replaced it, I didn't get rid of it. This condition still applies. So what's going to happen is that when we actually do the graphs, and we're trying to find valid values for k in order to find valid energies, the valid solutions for k are going to be the ones for which the resulting graph that we graph up has the wave function go to 0 at 1. It's just, so this condition is still true. It's just getting buried under this condition because ODINT doesn't like to work with systems where the initial conditions have non-arbitrary start points. So because of that, this is getting buried into the background, but it still does apply, and it's actually how we're going to use, it's actually sort of the qualifier that we're going to use to find valid solutions for k. So let's now do this on actual Python, because we already know the actual form of k. We know that the energy solutions are En is equal to n squared pi squared h bar squared over 2ma squared. So if this is equal to k, because k is equal to 2ma squared times e over h bar squared, or at least, so this is our definition of k from our ODE. If we plug in the accepted values for the energy of an infinite square well into this, we get 2ma squared over h bar squared multiplied by n squared pi squared h bar squared over 2ma squared. So this term cancels with this term cancels with this term, therefore k is going to equal n squared pi squared. So the valid solutions for k we're expecting to equal k1 is equal to pi squared, k2 is equal to 4 pi squared, k3 is equal to 9 pi squared, and k4 is equal to 16 pi squared. And, you know, up to 5 sig figs, these values are going to be 9.8696. This is going to be 39.478. This one's going to be 88.826. And this one's going to be 157.91. So what we're going to do is we're going to plug each of these numerical values for k into our code, look at the graph, and verify that the graph does indeed go to 0 at psi of 1. So I will meet you now on Python, and we will do this code actually. Okay, welcome to Jupyter Notebook. Let's start. We're going to do the same thing that we do always, just as we've done for 2.55 and 2.56, which is to import all the stuff we need. So import numpy as np from scipy.integrate, import odint, and then finally we want to graph stuff, so import matplot library.pyplot as plot. Okay, now that we have these, let's define our function. Define f of u comma chi, which I'm going to type out as e, and then this is going to return u1, and then negative k multiplied by u0. So once again, I'm assuming prerequisite knowledge from the previous two problems on how this is set up. Finally, the initial conditions, y0 is going to equal 0, 1 for the fact that psi of 0 is equal to 0 and psi prime of 0 is equal to 1. And then we define our graph. So I'm going to define an xs as linspace. So this is setting up my x-axis going from, in this case, instead of going from 0 to 10 like we did for the previous problems, we're doing 0 to 1. Because remember, we want to look at the behavior of the graph at psi of 1 to see if it goes to 0 or not. And we're going to do this in 200 steps. Then us is going to equal odint. So this is going to be solving my wave function to graph the y-axis. F y naught xs. Then actually getting the values for my y-axis. Ys is equal to us going next like that. Whoops. There we go. And then finally the plot points. So plot xs ys as a line. Plot x label, and I call this chi. And then plot dot y label wave function. And then let's plot dot show. And then finally, let's start assigning k values, because remember, we need to assign an actual k value. So the first one we're going to check is going to be 1 pi squared, or 1 squared pi squared for the first excited state, or the ground state, I suppose, because the 0th state is trivial. And this is going to be 9.8696. So we run this. Oh, whoops. Missed a line there. Or no, I just forgot a comma. There we go. Okay, so this one does indeed seem to go to 0 at x, or at psi, or at chi is equal to 1. So this is indeed a valid solution for k. So therefore, this one checks out. Next one, let's do 39.478 for the 4 pi squared. 39.478. We run this one. We see this one does indeed also go to 0 at chi equals to 1. So this one is also valid. The second solution, the second excited state is valid, or the first excited state is valid, sorry. Then 88.826 for the second excited state, which is, this one is 9 pi squared. This one also goes to 0, so this one's also valid. And then finally, the 16 pi squared term, 157.91, which also does indeed go to 0. So these four first, these from n equals 1 to n equals 4 states are all valid. They all check out via wag the tail. Sorry. So therefore, we have verified via sort of Jupyter and online programs that this that our original solution that was done by hand is indeed correct. And with that, we are done with this series of sort of Python-based problems.